A certain engine can propel a 1,800 kg car from rest to a speed of 27 meters per second in 9.5 seconds with an efficiency of 27%. A. Calculate the rate of heat flow into the engine at the high temperature. B. Calculate the rate of heat flow out of the engine at the low temperature. This question is about the heat engine. We know that the heat engine must operate at between two temperatures. One is a high temperature and another one is a low temperature. At the high temperature, the heat will flow into the engine, and at the low temperature, the heat will flow out from the engine. So the questions ask about the rate of the heat flow into the engine. Rate means in every second. What is the amount of the heat flow into the engine at the high temperature? Similarly, the question also asks us to find what is the heat flow in every second out from the engine at the low temperature. Now, these engines, heat engine, produce the useful work where it causes a car to start to move from rest to a speed of 27 meters per second. The entire process, that means for the cars to start from rest to achieve the speed of 27 meters per second, it takes 9.5 seconds. The efficiencies of the heat engine is 27%. Now we start to solve the first part of the questions. We need to find out what is the rate of the heat flow. That means in every second, what is the quantity of the heat flow into the engine at high temperature. So we find out first what is the useful output work. This engine makes the cars to move to gain the kinetic energy. So the useful output work is equal to the kinetic energy change of the car, or kinetic energy gain of the car, because this delta K is a K final minus K initial, and the initial speed of the car is 0, means that the initial kinetic energy of the car is 0, and the final kinetic energy of the car is half mv squared, where the v is a final speed, which is 27 meters per second. So this is the amount of the kinetic energy gain by the car. So this delta K should be equal to the useful work produced by the heat engine. That is why we write it as W output work equal to delta K. The process of changing the speed of the car from 0 meter per second to 27 meter per second, the whole process takes 9.5 seconds. So now we want to know about the rate. So we divide the output work by the time, delta T, and the delta K also we divide by the delta T. Rate of the output work, then we express it by P out. That means this is the power of the output. And at the right hand side, this is the delta K is a half mv squared, which is the final kinetic energy of the car. Delta K is the final kinetic energy minus initial kinetic energy, but initial kinetic energy is equal to 0. That's why delta K will be equal to the final kinetic energy of the car, which is a half mv squared. So V is the final speed of the car, m is the mass of the car, divided by the delta T. So this one, we call it as the equations number 1. Efficiencies of the heat engines of the car is given as 27%. By definition, we know that this efficiency is equal to the output work divided by the QH. This QH is a heat flow, quantity of the heat flow into the engine at the high temperature. H refer to the high temperature. We now divide the output work by the delta T, and the QH also divide by the delta T, so that we will have the eta in terms of the ratio of these two power. Numerator, this is the power output, and denominator, we call it a pH, is the rate of the heat flow into the engine at the high temperature. So this is a pH is the things that we want to calculate in the part A. That's why now we change the pH as a subject of the equations. We will get 1 over eta multiplied by the power output power, P out. From equations number 1, output power is mv squared over 2 delta T. We substitute into here, we will get mv squared over 2 eta delta T. We can now substitute the value. For m is the mass of the car, 1800 kg. V is the final speed of the car, 27 meter per second. Eta is the efficiencies of the engine, 27%. That means it is 0.27. And the process of changing the car speed from 0 to 27 meter per second, it takes 9.5 seconds. So we divide by this delta T is 9.5 seconds. Finally, we obtain pH equal to 2.557 times 10 to the power 5, or approximately 2.6 times 10 to the power 5 watt. The unit is watt. The unit for pH is watt, because pH is the power concept. It is referred to the rate of the heat flow. It means in every second, what is the heat flow into the heat and into the engine at the high temperature. Now we can start to find out what is the rate of the heat flow out of the engine at the low temperature. This is about the heat flow out of the engine, which is the QC. C stands for cold. It means low temperature. So it is related to the QH and the output work by these equations, where the heat flow into the engine is equal to the summations of the heat flow out from the engine plus the output work. Similar to the situations in the part A, since we want to know about the power concept, so now these three terms, all we divide by delta T. Now we have the relationship between these three power concepts. pH equal to PC plus P out. And because we want to find the power of the heat flow out of the engine, that means we want to find the PC, so we change the PC as a subject of the equations to get the pH minus P out. But pH, this value we already obtained in the part A, and this P out, mv squared over 2 delta T, also we already have it. when we solve the part A. We can substitute the value for the m, v, and delta t again. And finally, we obtain the PC equal to 1.866 times 10 to the power 5, or approximately 1.9 times 10 to the power 5 watt. This is a PC. It's the rate of the heat flow out of the engine. So PC again, this is the power concept. Is about how fast the heat flow out of the engine. So from our analysis, we already have three values: the P out, pH, and the PC. Again, this P out, pH, and PC are power concept, means that they measure how fast the heat flows and how fast the work is done. This whole process of changing the speed of the car from 0 or from rest to 27 meter per second, the whole process takes 9.5 seconds. So according to this result, we know that in every second, on average, the useful work produced by the engine in every second is 6.9 times 10 to the power 4 joule. And in every second, on average, the heat that flow into the engine is 2.6 times 10 to the power 5 joule. And in every second, on average, the heat flow out of the engine is 1.9 times 10 to the power 5 joule.